All right, welcome back. Right now, we're going to mention how we make carboxylic acids, and I'm going to try to walk you through the mechanism that makes that happen. Um, Now, specifically, we're going to focus on the primary alcohols that if you use a strong oxidizing agent, it will take you all the way to the carboxylic acid stage. Obviously, we don't want to start with methanol because the carboxylic acid is not the final stage, it's CO2 when you use a strong oxidizing agent. So let's take a look at the primary alcohols that make carboxylic acids with strong oxidizing agents. All right, so uh, the one we're going to look at initially is going to be permanganate. Now, permanganate, if it does accept 2 electrons, what basically will happen is that you end up with manganese 5, and the charge here will be 3 minus. So you end up with this intermediate when the first set of electrons is accepted by manganese 7. Now, what happens here is that this is what we call a metastable substance, much like manganese 6 plus, which is shown here in the red box. What this is telling us is that the substance is metastable and it will disproportionate into the higher oxidized species and the lower reduced species. And so this is going to ultimately disproportionate into manganese 4 oxide and permanganate. So you get a little bit of it back. But the ultimate fate is that you're making that manganese 4 oxide product. Okay, and what happens is very similar to what we saw during the reactions of alkenes and alkynes with permanganate. You basically rupture, the alkene and alkyne. But the first step is that you have to have something binding. And in this case, you do have an oxygen atom in your alcohol that has electrons, right? So those lone pairs can attack the manganese center. And basically what happens is that now you're going to have a proton exchange. So this proton that you have on the alcohol, once it binds to the manganese, it becomes very acidic enough that the hydroxide can actually remove it. So you'll have the hydroxide attacking that proton and moving the electrons onto that oxygen, and now you form manganese 7 alkoxide. All right, now what's important to notice right here is that the alcohol, being primary, is going to have hydrogens on the alpha position over here. And I'm drawing one of them out right there just to show you that what happens next is actually an interesting kind of situation. Technically, the manganese takes electrons from one of the oxygens that's already bound to it, but at the same time that prompts the CH bond to be ruptured. In particular, you passed on an entire hydride anion. So H plus the 2 electrons, 1 minus charge, gets added to this oxygen. And at the same time that happens, the electrons on the manganese are being, dumped, into the manganese, reducing it. At the same time, the carbon right here becomes electron deficient because the moment you remove that CH bond, this carbon now has less than 8 electrons. In order to make up for that, the bond between the oxygen and the manganese of the alkoxide is moved over here to produce a double bond. And so what ends up happening is that now you produce your aldehyde. All right, now, technically speaking, this is now manganese 5 that we're going to be forming, but the manganese 5 can be replaced by another equivalent of permanganate. And so the aldehyde can now bind to that new permanganate molecule and be at the same topologic. We have hydroxide is still present in solution because this is done under basic conditions. The hydroxide is going to attack the carbonyl over here to give us a species that looks sort of this way. And this is something you will definitely see a lot in Chem 256. So consider this a little preview, as well as, second year organic chemistry. So what's going to happen right here is that you form this tetrahedral intermediate. Okay, so that's going to require right here. And you still have that extra CH bond that you had to begin with because the carbon right here was primary. Well, once more, you'll have the CH bond entirely take off as a hydride. That will be given to the oxygen down here. The electrons of that manganese oxygen double bond will be taken by the manganese entirely to produce manganese 5, and in the process the manganese oxide bond is going to relocate to form a double bond with this carbon to prevent it from being electron deficient. And simply what that means is that you'll end up forming a carboxylic acid in that process. So the entire basis for this type of reaction is that you are basically stealing a hydride away from your alcohol, and it's kind of phenomenal to think that that this thing happens, because normally a CH bond is very strong, and breaking it is not an easy task. So what this is basically telling you is that permanganate is a very strong oxidizing agent, and you have to be careful when you handle it among organics, because if you're not, you could end up producing some serious side reactions that you may not want to be dealing with, um, for sure. Okay, but here the outcome ultimately is that as long as the carbon that bears the OH of the alcohol does have hydrogens, those CH bonds can be removed. Another way to think of this too is that yes, this is a carbon hydrogen bond, but it is a carbon hydrogen bond on a carbon that has oxygen bound to it. So they are a little less, um, a little more susceptible to be removed because the pKa's are lower somewhat. Okay, and that kind of helps a little bit with the removal of the CH bond. Okay, now ultimately what you do to get to the final products is to acidify everything, because you do have basic conditions. So you do add acids to neutralize the base, but at the same time the acid will react with your either chromium or molybdenum, and that will also help reduce that material somewhat. But end result that I want you to realize is that primary alcohols will go up to the carboxylic stage when treated with strong reagents, whether it is chromate, dichromate, or permanganate. That's irrelevant. All of them will make the same organic product. Okay, let's take a look at the ketones. In order to make the ketones, we do have to start with a secondary alcohol. Okay, so these are the things you need to remember. Primary alcohol goes to carboxylic acid. Secondary alcohol goes to ketone. Methanol goes to CO2. Tertiary alcohols don't do anything. All right, so the secondary alcohol, so here I have cyclohexanol reacting once more with one of the strong oxidizing agents like permanganate. The same thing that happened before will happen here. The alcohol will bind to permanganate. The proton will be removed by one of the hydroxides present in the basic solution. And then the manganese 7 will proceed to carry over the process of CH abstraction, um, which will be supplied as a hydride to the neighboring oxygen, which then supplies its own 2 electrons to the manganese, reducing it to manganese 5. And then the manganese oxide bond relocates to prevent the carbon down here from losing its octet. In the process, you end up forming a double bond, of course. And manganese, once again, is going to end up forming manganese 4 oxide, whereas the chromium, if you do use chromium, it will produce chromium 3 plus as the final product. As you can see in the predominance diagrams here, the standard electrode potentials of chromium. Okay, so that's basically it. Secondary alcohols make your ketone, and it's via the same process. You only have one CH bond on the carbon where the OH functionality is located. Therefore, you only have one acidic enough hydrogen atom that can be removed. All right, so that brings us to the aldehydes. Now, in order to make aldehydes, we can start with methanol, we could start with primary alcohols, but we're going to have to use mild reagents because this is only the first step in the oxidation sequence. And if you were to start with a secondary alcohol, the mild reagents will also be able to oxidize the secondary alcohol into a ketone. All right, so let's see how this goes. If you do use pyridinium chlorochromate, or PCC for short, this is still a high valent chromium species. So the first step is exactly the same as I showed you in the previous examples. The oxygen binds to the chromium. You end up forming, you deprotonate the alcohol, so you form the alkoxide. and then you have to give away that CH bond, right? So that hydride is given to the neighboring oxide, which has its 2 electrons supplied to chromium to reduce it to chromium 4 initially. Eventually it'll get turned into chromium 3, and this will produce the aldehyde. Now, if this reaction is done in water, there is nothing stopping you from getting to the carboxylic acid, because you do need to have hydroxide to attack this aldehyde, produce the 2 oxides on this carbon in order to allow the reaction to proceed forward to the carboxylic acid stage. But if you perform this reaction in methylene chloride, which is an organic solvent where hydroxide not only does not dissolve but is completely incompatible, then the second step is no longer happening. And if you don't get that hydroxide in here to continue the process, then you stall the process at the aldehyde stage. So the lack of water is what prevents PCC from oxidizing this material all the way to the aldehyde stage. All right, now, aside from that, chromium compounds, especially highly valent chromium compounds, are rather toxic and difficult sometimes to isolate from the organic products. So that makes it a little less ideal to to use it practically in a synthetic lab. So that's where the reagent right here, the MSO plus oxalic chloride, will come into hand. And this, by the way, is known as the Swern oxidation. And I'm going to show you the mechanism of how this works. First, DMSO attacks with its oxygen one of these carbonyl carbons. Now what ends up happening first is that the double bond, the CO double bond, is broken after addition of this nucleophile. But then the oxide that you just formed right here by breaking the double bond gets reformed. So you reform that double bond, all the meanwhile kicking out the good living group chloride. And that gets you to this molecule right here. And of course you still have the chloride hanging around. Now the chloride, which originally was on the organic substrate, attacks the sulfur atom. And that basically prompts the sulfur oxygen bond to be broken. In fact, the electrons get moved over to the carbon next door. Now that carbon already has a full octet, so you have to break one of the bonds, and the bond that you end up breaking, interestingly enough, is the carbon-carbon single bond, which brings its electrons towards this carbon. And what that means is that now you have too many electrons on the carbon, so you have to break another bond, and that's the chlorine, the carbon-chlorine bond that breaks. And at first you may see this and say, well, this is kind of weird. Like, why wouldn't you just break the double bond, the pi bond, which is weaker than, the sigma bond? Why would you do this? And the reason why is because if you look carefully, bringing these 2 electrons over here and breaking this carbon-carbon single bond will produce CO2, which is a gas. And at the same time, bringing these 2 electrons over here to this carbon and kicking away the chlorine group will produce carbon monoxide. And once you form those 2 gases, they're gone. So this is kind of the driving force for this process. You form the gases and the gases take off. Okay, so now that takes us to this stage. This is the actual active species that will do the oxidation of your alcohol. Okay, so dimethyl chlorosulfonium ion. All right, so here we have the alcohol, which will interact with the sulfur cation that we have right here. So the oxygen will attack the sulfur, chlorine will take off as a leaving group, and then you'll have one of the chlorides remove the proton to give you an alkoxide. Okay, so here's the part of the mechanism that is tricky, and I recommend that you practice drawing this mechanism a number of times just to kind of keep it fresh in your memory, because even I from time to time I forget. It's like, oh, that's right, yeah, we're gonna mess up and mess around with this carbon on the alpha position, because now what happens is that this sulfur with a positive charge makes this CH bond rather acidic, more acidic than you would expect, uh, specifically to the point where the chloride can now attack this hydrogen and produce a carbanion. All right, so now we have a lone pair on that carbon, and this is plus, minus, technically this is neutral. Okay, but here's where the process now proceeds to go forward. The carbon ion is still a basic substance and highly basic, um, might I add. So this basic carbon ion is going to attack the hydrogen on that alpha position of the alkoxide. And then the electrons over here will have to move over to the oxygen, which means that the sulfur oxygen bond will have to break. The electrons in essence will have to be given to the sulfur. And when this all happens, you'll have forming um, not sulfur dioxide. That's a tiny little mistake. This is dimethyl sulfide actually. So dimethyl sulfide is the gas that you'll produce that will be gone, and in the process you will also form your aldehyde. And at this point the Swern reagent is no longer there. It's gone. All of it is gone. Oxalyl chloride has been turned into CO2, carbon monoxide, and then your dimethyl thionyl chloride cation has been turned into dimethyl sulfide gas. Okay, so this is the entire mechanism. Make sure to practice it. It is a complex one, and you will be asked about it in examinations in the future. So make sure to practice it. All right, now what I want to do to finalize this video is to kind of give you a little table summarizing everything that we've done. We have oxidizing agents, right? Mild and strong. And for the mild ones, we have the Swern reagents, the DMSO oxalyl chloride combo, as well as PCC in organic solvent, specifically methylene chloride. In other words, you want this to be as anhydrous as possible. So what happens is that for methanol, you will produce a certain molecule. Oh, but first let me also introduce the strong oxidizing agents. The strong oxidizing agents will be permanganate in basic solution. Heating may be involved, maybe not. That depends on the circumstances. Chromic acid, dichromate, PCC in water. All of those are strong. So methanol with a mild reagent will form formaldehyde. A primary alcohol will produce aldehyde. A secondary alcohol will produce a ketone, and a tertiary alcohol does nothing. And that's true for the MSO oxalyl chloride or PCC and methylene chloride. Now if you use a strong reagent, the methanol will be turned all the way to CO2. Primary alcohols will be turned into the corresponding carboxylic acid. Secondary alcohols will still produce the ketone, and your tertiary alcohols, no matter what, will not give you any new product. So keep all these things in mind. This is just a summary of what we expect to observe. You still need to apply it to the specific molecule that you have at hand, and be able to predict those products just by looking at the reactants and the oxidizing agents that you're using, and vice versa. Be able to predict the reactants from which the products are formed given the oxidizing agent. And the only other alternative will be to determine which oxidizing agent you're going to use if you're given the reactant and the product. So those are the things that you have to think about when it comes down to this type of process. Okay, so with that being said, we'll stop the video right here, and in the next one we'll talk about reductions, specifically reductions with hydrides. So see you in the next video.